Hey there, awesome physics students. Let's talk about how to solve problems with Newton's second law. I have a nice problem-solving framework I want to show you, but to demonstrate that, I want to start with an example to show you that problem-solving framework. So let's talk about our example first. Imagine that you have a canyon that a person is traveling across, and they've spanned a rope across that canyon, and they're hooked in, and they're moving hand over hand across the canyon with the rope. So they're at this particular moment they're hanging from the rope. The rope is at an angle of 15 degrees from the horizontal on both sides, and the weight of the person is 800 newtons. So that's the force of gravity on the person. And our goal here with this problem is to find the tension in the rope. Okay? So let's talk about how to do this. So the first step in our problem-solving framework is to draw a picture. And we've already done that here. So that one's done. We can check that one off. The second step then is to draw a free body diagram. And so let's do that. Here's our person. Of course, with the free body diagram, you always want to identify clearly which is the object of interest in this case and distinguish that from the agent. The object of interest is the person, so we want to run through all of the forces acting on the person. The person, of course, is near the surface of the earth, so they're going to have an 800 Newton weight, which is the force of gravity. So let's run through our other items here. Are they sliding? No, so there's no friction. Are they touching anything? Well, no, they're touching the rope, so there's tension from the rope, and that tension is pulling them in two different directions here. One more thing to note about tension: because this is one continuous piece of rope, the tension will be the same throughout the entire rope. Okay, so these two magnitudes of the tension are the same on both sides. They're pulling in different directions. Let's see, are there any other forces? There's no drag, and there's no normal force. So I think that's everything that we need to know about those are all of the forces for the free body diagram. So let's move to step 3. Step 3 is to draw the acceleration off to the side. Of course, you never draw the acceleration on the free body diagram itself because it's not a force. The acceleration in this case is 0 because the person is in static equilibrium. Their velocity is 0 and their acceleration is 0. So let's put the acceleration as 0 off to the side there. The reason we want to draw the acceleration direction is because the next step is to identify a coordinate system, and we want to align that with the acceleration direction, meaning one of the axes, like for example the x-axis, will be parallel to the acceleration, and the y-axis will be perpendicular. In this case, and in any case where you have acceleration is 0, you can use any coordinate system. So we usually use the standard xy coordinate system here. I'm going to put that up here. All right, so the next step here in our framework is to sum the forces in the x direction. And you do that, you have to use your free body diagram to do that. And then you set the results of that equal to mass times acceleration in the x direction. Of course, in this case, it's 0. You do the same for the y. You sum the forces in the y direction, add up all your components, positive and negative, in the y direction, and set that equal to acceleration in the y direction. So let's do these two. We'll spend most of our time in this part. So let's first sum the forces in the x direction. So for that one, we have the 800 Newton force is totally vertical. That's only in the y direction. So we have the horizontal component of the tension force here, and this is a 15-degree angle. So that's adjacent to the angle, and so that's going to be the magnitude of the hypotenuse there for my triangle is Ft. That's the tension force times cosine of this angle. I'm just going to leave it like theta for right now. because that's adjacent to the angle. And that's this one. And then I have another one over here. And that one points in the negative x direction because positive x is this way, negative x is that way. So this is going to be minus ft cosine theta. And those are the only two forces in the x direction. So that's what I mean by this dot, dot, dot part, is you identify all those components. Then you set it equal to mass times acceleration in the x direction. Well, the acceleration in the x direction is 0, so I just put a big fat 0 there. Well, this just tells us that the rope is pulling with equal forces this way and that way, which you could probably see from the diagram. So this is really not a very useful equation. Let's do our forces in the y direction. Sum the forces in the y direction. We have, of course, we'll start with the easiest one. We have 800 Newton force down, and that is in the negative y direction because positive y is up. So I put the negative sign there by hand. And then I have this component of the tension and this component of the tension. Those are both opposite of the 15-degree angle, so I'm going to use sine. So I have two of them, one here and one here. So I'm going to put a 2 out front. That's force of tension times sine of theta. I'm using sine because these two are opposite of that angle theta. That's 15 degrees. Okay, so those are all of the forces in the y direction, so I set that equal to mass times acceleration in the y direction. Again, that's 0. Put a big fat 0 there. I love static equilibrium. And so then that brings us to the next step of our point here. So after you do these, you're basically using Newton's second law to generate custom equations each time for each problem. For part 6 here, we want to count the equations and count unknowns. So what are our unknowns in this equation? Well, we know the weight, we put that in. We know theta is 15 degrees. We don't know, let me just concentrate on this equation here. We don't know the tension force. That's what we want to find. We know that. So we really have one equation and one unknown. And if you recall, if you have the same number of equations as you do unknowns, you can use algebra to solve that. That's why we're doing this. We're trying to figure out if we need another equation. In this case, the answer is no, we do not. Okay, so one equation, one unknown. Those are my favorite to solve. So we have enough equations. We don't need another equation. The last step here is algebra. Okay, so let's go ahead and do the algebra. Do the algebra on this one to find the tension. So I want to solve for this one. So I'm going to throw this on the other side. That's going to add 800 newtons to both sides of the equation. And I'll get 2ft sine of, I'll go ahead and put the angle in here, 15 degrees is equal to 800 newtons. And I want to isolate this, so I need to divide both sides by 2 and divide both sides by sine of 15 degrees. So let me do that. Okay, and so this tells us, of course, these are going to cancel and these are going to cancel. So I'll get Ft is equal to 800 newtons, and that's 2 times sine of 15 degrees. And when I punch this in my calculator and I get the number, I'll get, I did this ahead of time. I don't do this in my head like this. That's 1545 newtons. Okay, well, does that surprise you? The last step of our procedure here is a sanity check. Does this make sense? That seems really huge. But if you think about it, here, sine of 15 degrees, sine of 15 degrees is a small angle, and sine of small angle is really small. And because this angle is really small, you imagine if you shrank this angle, that vertical part would shrink. And then the magnitude of this would have to increase to make this vertical part big enough to offset the half of the weight, because you have half of it on each side. So actually this does make sense. If we made this angle bigger, so if sine of the angle was the the angle was bigger, and then sine would be bigger, would be dividing by a bigger number, and this tension would be a lot lower. So this tells you a couple of things. First of all, if you're going across a canyon, don't, for God's sake, leave some slack in the line there, because you don't want the angle to be really small. You want the angle to be pretty big so that it'll support your weight without having too much tension in the rope. That's one thing. And the other thing is that in these cases, the tension in the rope is going to be a lot bigger than your weight, because there's only a component of that that is actually offsetting your weight. Okay? So hopefully, so this last step here is, I think our sanity check is okay. So hopefully this gives you an idea of how to use this problem-solving framework with an example. Most of these problems are going to be the same steps every single time. Don't follow this like a recipe. It's just a set of guidelines to help you. And in many textbooks, you'll see very similar sets of guidelines like this. You'll see many of the elements in common. So I urge you to try and do it in an organized, systematic fashion like this. All right?